In this work, we present a method for multi-robot shared autonomy based on a set of expert demonstrations. In shared autonomy, a human and a robot policy share command over a physical robot platform. For example, in the sanding task on the left, the robot assumes the physical burden of sanding, while the human uses expert task knowledge to provide corrections to adjust the abrasiveness of the robot sander when it is not sanding correctly. One challenge in shared autonomy is that the robot doesn't require constant input from the human operator. Returning to the sanding example, there are parts of the task where the human's judgment is required to sand correctly, for example during any difficult curvature or on critical features. However, there are also many parts of the task where the human is not needed, such as when the tool moves over the surface, when the robot changes sanding disks, and when the robot sands simple geometries of the surface where there's not much variability. Particularly when the parts needing help make up a small percentage of the overall task, the operator is not well utilized. To improve operator utilization, we investigate scaling the operator to provide corrective input to 2 robots. Ideally, the robots would be coordinated such that the operator could only need to help one robot at any given time. This requires knowing what corrections an operator might provide and when during the task they may occur. In this work, we propose a scheduling method for shared autonomy that coordinates 2 robots around when they may need corrections. At a high level, our method centralizes around using expert demonstrations and Bayesian inference to schedule 2 robot executions. Please see our paper for the technical details. The robot behavior and corrections an operator can make are extracted from the demonstrations. We schedule the robots around times when they are high confidence, meaning that corrections are unlikely, and times when they are low confidence, meaning they might need corrections. We estimate the confidence iteratively. Initially, when the operator uses the system, most of the robot behavior is low confidence, meaning the robots will generally perform the task one at a time. As the operator completes more and more instances of the task, the empirical data of whether corrections are provided is used to refine the confidence estimate, so that the system can schedule more parallel solutions, where one robot executes high confidence actions while the other robot is executing low confidence actions. We formulate our scheduling problem as an optimization, where the constraints are the required properties of a valid scheduling solution, and the minimization criteria allows us to specify additional desired properties of the scheduling solution. For example, the constraints assure that both robots will not execute a low confidence action at the same time, even when the operator provides corrections that influence the timing of the robots. The objective function minimizes total time on task. Given the non-convexity of our scheduling problem, we solve the optimization by sampling the 2 robot behaviors and a start offset from the demonstration limits. We keep the solution that satisfies the constraints with the lowest cost. If no solution is found, we can fall back either to the robots serially executing the task or a previous scheduling solution. To assess our method, we ran a preliminary evaluation on a sanding task to demonstrate how the scheduling solution of the multi-robot shared autonomy evolves with simulated use of the system. Our sanding task was motivated by industrial sanding applications and consisted of 4 sanding passes. The first 3 passes were variable and had only 50% of the area painted in random patterns. The 4th pass was consistently painted. Consistent with the task, operator corrections would be required during the first 3 passes to address the paint variability. We collected a set of 6 demonstrations using an instrumented sanding tool. Using the demonstrations, we ran 5 trials with 300 simulated executions of the system with operator corrections. The simulated operator gave corrections 50% of the time during the first 3 passes. We also included a human error rate of 1%. Our results show how the percent of high confidence samples increases over use of the system, and how the system is able to find shorter scheduling solutions. Initially, most times are low confidence, and the robots execute the task one at a time. As the confidence increases, the system is able to find parallel solutions that overlap the variable sanding pass of one robot with when the other robot is moving between sanding passes. The final scheduling solution is 70% faster than the initial schedule. We also developed a prototype system to demonstrate our method. The setup consists of 2 Franka Mika robots with orbital sanding tools. Each robot has an LED ring at the end effector that indicates the confidence of the robot. The LEDs are red when a robot is low confidence and green when a robot is high confidence. In the future, we plan to use this system to run user studies to assess the usability of multi-robot shared autonomy and the impact of different minimization objectives on the human factors of the system. Summarizing, in this work, we proposed a method for multi-robot shared autonomy and demonstrate how our method enables users to efficiently share autonomy with multiple robots. In the future, we are interested in scaling our methods to larger fleets of robots, exploring practical and human factor considerations, and evaluating our method with users and a range of tasks.